All right. How are you doing? I'll just make a joke at this time. Back at it. This is the actual lecture. You say there's a lot of slides, and yeah, we may not get through all of it, and that's okay. I'd just like to get through the model comparison part first, and if we start next week with a little bit more, that's fine too. You don't need the tail end of the slides to do the homework. It's the philosophy of why the homework is there is what you do for it. And actually, in those little example snippets of syntax, you can weed out the syntax you need for the 4 models to run in part 2. I've already sort of given those to you in the homework document itself. There's your hint. But we'll start up here. So the goal is, this is kind of a weird spot. It's path models. I gave you a chapter from Klein to read about path analysis. And it's not quite multivariate normal, but it is. All right? Everything that we've done with a multivariate normal distribution or a univariate normal distribution is really what we're going to be doing with path analysis as well as we go forward. And I spend a lot of time in it because it's really how we go and sort of falsify the hypotheses that we're making in science. Right? So in the process of science, now again, I'm not a philosopher of science, and there are many of you who probably could teach something like that much better than I could, even if the Jimmy John's rappers were quieter. No, I'm just kidding. Sorry. But, sorry. I like to pick on you. That means that you please pick on me, too. I'm just trying to make it a lighter atmosphere in here. But the thought of this, every time you come up with a model, every time you put a regression, put a predictor into a regression model, you're making a hypothesis about the world. Path analysis is no different. It's essentially a very large set of hypotheses you're making all at once about the world. And the same thing with confirmatory factor models, measurement models, and structural equation models. All of those are lots of hypotheses all at once. And so what we're trying to do is come up with an alternative hypothesis. We've actually started this class by building the alternative hypothesis to everything that we're doing. What's that mean? Think of it this way. In a multivariate normal, if we're doing a multivariate analysis, maybe we have this flower data, right? We've got sepal width, sepal length, petal width, petal length. So we've got 4 measurements per flower. The question is, when we do a multivariate normal and we get a covariance matrix out of it, we're essentially saying each one of these measurements is unique by itself and cannot be synthesized. It cannot be condensed. We have 4 measurements. There are 4 measurements. To describe any flower, we have to know all about those 4. Alternatively, we could have come up with a hypothesis that says, yeah, we have these 4 measurements, but really what these 4 measurements are really indicating some other thing that we couldn't observe about the flower. There's some type of gene that is expressed in a certain amount of quantity, and if it's turned on, then all of these happen. If it's turned off, it's not, or something along those lines. All right, that is a much more structured hypothesis. And what we have just built by building these mean vectors and these covariance matrices is essentially the thing that would always fit best, right? There's nothing that could be better than saying, in terms of this world of models, multivariate normal with data, there's nothing that will outfit or be better fit than just saying every variable is important and all by itself, and there's nothing more we can do from there. That is by far the best fit. So when you build a hypothesis, like I just said about the flowers, your goal is to say, okay, I can't fit better than it, but does this hypothesis fit as well as that? Because if it fits as well as that, then I can at least say it's plausible this is the case, right? Maybe this gene expression part. But if it doesn't fit as well as that, I can say this definitely is not the case, and that's the falsification for it, right? So when you build a structural equation model, when you build a path analysis, you're setting out a large set of hypotheses all at once, and all the things that we've seen to this point, the unstructured mean vector and covariance matrix is essentially your alternative hypothesis, right? You need to fit as well as it. If you don't, your hypotheses don't hold, right? You have to reject them, which means you've got to change your theory or change. Usually what happens, it means we just play around with the model and try to get something that fits as well. We say, hey, that was my hypothesis all the way along. Anyway, we can get to that later. But why we're talking about this over and over and over again is because in a multivariate normal framework, when you assume your data are like that, it sets up what the alternative should be, right? It basically says, okay, this is a great falsifiable framework that you can take with your data and test whether or not that's true, right? If you're building a factor, maybe you have a confirmatory factor model. Like, I'm going to measure this one, maybe it's not flower data, maybe it's item responses or survey questionnaire responses, and you think there's one factor that underlies it. Or maybe you think there's 4, whatever. That's a hypothesis, right? What is the alternative hypothesis? You've just seen it. Saturated, mean vector, and covariance matrix, right? So that is H1. That's why H1 always shows up as in your output, because that's your comparison. So that's where we're going. That's why I'm spending all this time on this here. I'm also doing it in a broader sense because I'd like you to think that if that's the case for this distribution, and there are other distributions out there, there are other ways of doing it if your assumptions aren't quite met. So that's for later on, but that's where we're at here. So what we're going to talk about now is what happens with multivariate data, because in a multivariate analysis, so things are a little bit different than a regression model, a univariate analysis, in that with a mean vector and with a covariance matrix, there's a lot of terms, a lot of variances, a lot of covariances, a lot of parameters. And with that becomes is a problem. It's power, sample size, right? Did you collect enough data to estimate all that you want to? So these are the types of things that pop up, and today's lecture is a broader context about multivariate models, multivariate modeling. It would still fit in if you're taking a course on MANOVA, if you're taking a course on repeated measures ANOVA. We're actually covering those models today, although I'm not going to say those in the slides. I'll tell you verbally, that's a MANOVA, that's a repeated measures ANOVA. It's all in the same context, in the same umbrella. One step further, oh, it's path analysis. Oh, one step further, that's a structural equation model. So it's just trying to give you that structure. But everything we talk about today still follows forward. Model fit, right? How do you evaluate whether your model fits close enough to the alternative? And then later on, how do we build models afterwards? So, okay, what are multivariate models? Why is model fit important? What methods do we use for evaluating global model fit? What is global model fit? Local model fit. And if you find that a model fits, what does that allow you to do? I guess you're allowed. It sounds very paternal. Allow. Maybe that's not the word I'm looking for. Dogmatic. Oh, you're not allowed. It's very. These are the rules. But no, it's more just what can you claim about it? If a model fits, what can you claim? What can't you claim? Basically, I'm working towards the C word here. Causality. I know what you're. Some of you were laughing over here. I know causality is really funny. But causality is really a dirty word. You'll never be able to do that unless you have everything right. But I'll talk about where that filters in if you get model fit. Okay, that's in opposition to others that you'll see talking about. Sometimes structural equation models are called causal models. That's what I say to that. Okay, so to help with today's class, I grabbed a paper by Pajares and Miller. And believe it or not, one of the students of these folks is a postdoc in the AAI. And she and I are working on another data analysis that she's going to submit as a paper. And she cited this paper. Just yesterday, I was reading about Pajares and Miller, this paper that I pulled out of the literature in a Google search like 2 years ago to create an example. So I grabbed this paper. It's the role of self-efficacy and self-concept beliefs in mathematical problem solving, right? A path analysis. I grabbed it because I searched for path analysis in education. Okay, that works. Let's see if we can pull these two together. They took a sample of 350 undergraduates with that proportion of men and women, and they had 10% of roughly 10% of their variables were missing. And I just went and took their paper and I simulated data according to what they said the model should be or what the results should be. So from their model, it implied a mean vector and a covariance matrix, and based on that, I could generate multivariate normal data. So that's what I did. Pretty awesome, huh? Right? Anyway, that's the other part to it. We're actually implying these distributions. You can go and check. You can generate data and see if it looks like your data. So here are the variables. There's a lot of them. We're sort of going through them one by one. Ultimately, we're getting to something that looks like that. That is a path diagram. And we will talk about this thing next week. But essentially, this is the set of hypotheses that we build into path analysis. And in a short, to look at something like this, wherever you see a box, that is an observed variable, and in our context, we are treating these as observed without error, which is not true in our case, but we're just going to pretend that way. Whenever you see an arrow that ends at a box, like right here, that means that that box itself, this thing, is a dependent variable, right? So it's implying a regression line. So for instance, math self-efficacy is a dependent variable, and it's being predicted by three things: high school math experience, gender, and college math experience. In fact, if you look this over, I know there's 7 variables altogether, 6 of them are dependent variables. And the lines represent what we call a direct effect. That is literally what we would call a beta weight, right? That variable predicts this other one. The independent variable predicts a dependent variable. Now, one thing that you might think is a little odd, this math self-efficacy is both a dependent variable and an independent variable, right? It's predicting math self-concept, math performance, and perceived usefulness of mathematics. Right? So it's doing a whole bunch of things, and that's fine. In the path analysis, you can build this. It's just a series of regression equations where some terms are dependent and some are independent. Gender is not dependent at all. Next week, and if you, I think in the Klein chapter it said the words exogenous and endogenous. It didn't actually define them. That was a chapter before that. This is where the definition comes from. Anything that is a variable that is being a dependent variable in a model like this is called endogenous. Right? It's in the model, even though it's endogenous, endogenous. That's my mnemonic for it. If it's being predicted, it's an endogenous variable. Even if it predicts other things, so long as you see an arrow terminates at it, it's in the model, it's a dependent variable, it's endogenous. That is as opposed to a variable like gender right here, which we would call as an exogenous variable. It is external to the model itself, which means it may vary, but we're not going to describe or explain why it varies. It's just that it varies, right? Clearly, gender varies, right? We don't need a model to describe why it varies. We just think that it's enough. So as long as we know what your gender is, we might be able to predict how much experience you had in high school or what your self-efficacy for mathematics might be. So that's what this big picture is doing. That's where we're going. You can look at all the variables here. I wanted to start a little bit more simple. Start with univariate regression again. Let's start with mathematics performance. The performance variable, which is over here at the end, that thing, is essentially a 20-item math test they gave people. It's the score out of 20. We're going to pretend that's measured perfectly for right now. In structural equation modeling, we would never do that once we get to latent variables and constructs. But for right now, let's imagine, hey, 20 items, perfect. Okay? I like that. I like pretending. A lot of science is pretending. At least a lot of the modeling work that people do in the sciences I'm familiar with seems like it's pretending, but it happens. So here's an empty model. Right? We're saying performance is equal to an intercept plus some error term where the error has a variance. What does the intercept represent then in this empty model? The mean, thank you. The mean performance. What does the error variance represent? The total variation. Right? So here are the parameter estimates itself. The syntax for it. We see that the mean, on average, people got 13.9 points out of 20 on this math test. So what is that? Can't even do math now. A little less than 70%? Something like that? Did I get that right? Yeah. Okay, so I took that, and we've seen this with data, right? I want to connect model to data. That's what a lot of this class happens to be. So here's a histogram of our performance data. The dotted line is a smooth, what we call a smooth distribution. It's essentially, if we were to create a relative frequency out of our observed data, what would it look like? Right? And then the smooth line is the denorm function in R. So I created all this with R. I just wanted to overlay it. And you would say, yeah, doesn't our model look like our data? This black line essentially incorporates most of our data. It looks pretty normal, right? But that's very rare. These data, remember, were simulated, so part of the reason for that. So that's what we want. We want our model to represent what's happening in our data. Right? We never ever leave the world of data, even though we get far away from it. We talk about parameters and estimators and all these other things. The data are the thing that govern everything, and that's where we never want to leave it from. So what we're going to do now is we're going to move from one variable to two. So that was a univariate empty model. What if we had two variables? It's now a multivariate model. Right? I made a mistake. Perceived usefulness is the variable that's denoted by the word use right here. So we're going to assume both of those variables are continuous and measured without error. And we're going to look at what happens when we go from this univariate regression with an empty model to a multivariate regression with an empty model. And sure enough, you will have seen the result before. Right? If the univariate model gave you the mean and the variance as its parameters, right, which map onto a univariate normal, what do you think the multivariate model gives you? Or better yet, what distribution does it map onto? Multivariate normal. And what are the parameters of the multivariate normal? Mean vector, the means for each, covariance matrix. So variances and covariances. And that's it. Right? We go from one to more than one. We have the same approach. Mean vectors, covariances. I mean, covariant means and variances, but now we add in covariances as well. So, just like in an empty univariate model, the empty multivariate model gives us a baseline from which we can describe how much variation is explained. Right? So we look at in homework one. This is why homework one had that question about R squared, and I had you fit the empty model and then the one before it, and you could tell with the residual variance, you could hand calculate R squared. You could see it, right? It's not some mythical thing. It's just a ratio. The same thing works for the multivariate model. There is an R squared now for each variable. Right? It comes from the diagonal of the covariance matrix. So we'll also be able to look at this empty model for in the didactic sense of teaching in this class, to talk about model fit, characteristics of the multivariate normal distribution, where a model should look like based on our data. So there we go. The bigger picture is how when we do more than one, we're not guaranteed to be saturated with all of our parameters, right? In a univariate model right here, we had a mean vector, we had a residual variance. Believe it or not, it was saturated. Remember the word saturated or unstructured means every parameter's been estimated? All of the univariate regressions you've had have always been the unstructured model. They've always been it. You never were told that because you never thought there was anything else than that. But when you get to more than one, not all of the models are that way. So what we have to do is, first of all, identify if our model is that way. Because if it is that way, it needs to fit as well as the unstructured model. Right, so that's how we have to be sure we're doing the covariance matrix modeling correctly. Questions? Big picture questions. I'm going to have another Coke Zero in my Royals Coke. Spring training starts this week? Next week. Next week. I normally wouldn't care, but last season was pretty cool. So, all right. What's the univariate model look like? The multivariate model, it is, instead of one regression, it is now two regression lines. One for performance, one for usefulness. And if we were to look at either by itself right here, it would look just like a univariate regression, although now I add the word in superscript what's predicting to it, PERF. That's because when we start doing path analysis, we'll have multiple dependent variables, multiple endogenous variables. So I like to denote which of my effects are for which kind of regression equation, right? So this beta 0 perf represents the intercept in the prediction of performance. Beta 0 use represents the intercept in the prediction of usefulness, right? They're both intercepts, but they will likely be a different value, and they will likely be, in a different model. So similarly, we also have each one has a residual or an error term. And now, because we have more than one error term, univariately, if this was a univariate model, we'd say any one of these was a normal distribution with some error variance, right? We would estimate. But now, because we have two of them, we can put them both into a little vector here. Is that a column or a row vector? It's a column, right? 2 rows, 1 column. That now would follow what we would call this normal distribution, and sometimes I put the number of dimensions, so n2 represents a bivariate normal or a multivariate normal with 2 variables in it distribution. So now we're saying error follows a multivariate normal distribution. We have more than one error. We can be off in the performance direction, we can be off in the usefulness direction. And just like we would assume in a univariate model, the mean for each of those error terms is set to 0. It's fixed. So if you remember that matrix, that riveting matrix algebra lecture, that's sarcasm. This thing in 0, the 0 with bold is the 0 vector, right? So that's that. But now, because we have 2 terms, we'll need a covariance matrix. Sometimes we call this R. In fact, if you're in the mixed model world, or HLM's world, you would call this the R matrix. Weird. But R for residual. It's on your residual variation. Right? And it contains in it, in the top part, the residual variance for performance. The lower right diagonal is the residual variance for usefulness. And the off diagonal is the residual covariance. So this first number, top left diagonal, is how much variation there is in your prediction of performance. Once you've predicted performance, how far off are you? Your offness once you've predicted performance. This is how far off you are, or variation in it, once you've predicted usefulness. And finally, this covariance is essentially saying if you're off on one, is it related to how far off you are on the other? Right? So if it's positive, it means if you're high, if you predict too high on performance, you predict too high on usefulness. If it's negative, you predict too low on one, predicts too high on the other. So it's a little weird concept to think about in some respects, but let's think about this from the terms of the empty model. Right? In an empty univariate model for performance, we just decided that this beta 0 performance was the mean of our performance variable. We all agreed, right? Homework 1 declared that. I know this because most of you got that. In fact, all of you got that right. Sigma squared error for performance was the variance for performance. Right? And so similarly, we would think that beta 0 usefulness, sigma squared error for usefulness is the same. Mean of usefulness, variance of usefulness. And sure enough, it is in a multivariate sense. So if all these check out, they're the same interpretation univariate as a multivariate. What is this term right here then in the multivariate empty model? It's our estimated covariance. Right? That's it. Hey, it's our estimated covariance matrix. That's it, the population covariance. Now remember, covariance is the spike of Snoopy's correlation. Do I need to remind you of spike? Do I need to ask Google? No, I'll do that later. All right, so we could take this and use these numbers and come up with the estimated correlation for it. But we have it here. So that's it. That is a multivariate empty model. Sure enough, it is the same thing. It is our saturated. It is what our data says in a multivariate sense happens. And that's what you're doing with your homework this week, right? The saturated model, which is Model 3 of Part 2 of the homework, or Question 1 of Part 1 of the homework. Those were saturated, right? Those were all the terms you could estimate were all in there. That's it. That's it right here. If we wanted to put a little bit more matrices in it, we could. I'm not going to go too far. We could. This is just tying it to matrices. One thing I'll note is, in a general sense, when we assume something about the error part of a distribution in this linear model, we're actually making an implicit assumption about y itself, our outcome data, our dependent variables. And that assumption is that once you condition on x, this is the distribution of y given x. Sorry about my notation here. Once you predict y with x, that y is multivariate normal. in that sense, that distribution variance and the covariance of y is v. I'm just going to leave it for now. That doesn't matter as much for us. But what does matter is this. Here is our model. Actually, it does matter. Gosh darn it, template. There we go. So when we get there, basically, if we say y given x is this, what we're saying is the mean of y, the mean vector of y in this empty model is given by performance and usefulness. And the covariance matrix has 3 terms in it: sigma squared error for performance, usefulness, and then sigma for the 2. The variance of performance, the variance of usefulness, the covariance of performance and usefulness. So there's our 5 terms. And what now I'm going to do is try to map all 5 of those terms onto Lavaan syntax. Right? So in Lavaan, if you want to be explicit, you can access every single term in the multivariate normal in the syntax. That is what is built in. Now, up to this point, I haven't been showing you all of the syntax because it gets verbose. If you just access one of those terms, it implies the rest. Right? Had you just said, I wanted the covariance between performance and usefulness, it'd give you all 5. But you could put all 5 in syntax, and that's what this is trying to say. The mean vector, so we know the variance term, this double tilde term in Lavaan syntax. If you put a variable on either side of it, it gives you the variance of it. So that is the performance thing, the variance of performance. Same thing with usefulness. And if you put a different variable on either side of it, you get the covariance. You can also get access to the means themselves. Now that seems a little weird, but we can. That is with this, what looks like the regression syntax. And sure enough, it is regression syntax. The 1 is the intercept, and that gives you the mean of performance. So use tilde 1 is the mean of usefulness. Right? So Lavaan, and actually M+ and all the other structural equation modeling packages that you would come up with, really is trying to get you in syntax to declare what each of the terms in the multivariate normal are. So it then can go estimate your model itself. So hopefully this is tying together why we did multivariate normal a little bit ahead of time. So this is the saturated model. And remember, it's also called unstructured. So sometimes you'll see saturated, sometimes we'll see unstructured. Lavaan may call it unrestricted. There's lots of terms for it, but basically everything's free to be what they want. Right? You estimate everything. That's a lot. But remember this, right? This is the alternative model. This is saying everything, nothing can fit better than this. In this world, when you just look at multivariate normal, when you just have one, observed data, no latent classes or anything else, nothing can fit better than this structure right here. This is the pinnacle, right? It is describing, it's basically saying every variable has to be accounted for by itself, and then we also need to account for every pair of variables because they all covary. That's it. So here are our estimated values themselves. Side note, why is the sample size different from Model 1? The reason for that is when we do a multivariate normal, we now have that. Remember how we talked about missing data at the end of class? We skip it in the likelihood, right? So basically, if we only had one variable in our empty model, that meant if somebody was missing on it, they were out. But now when we have 2, that person missing on the first may have an observed value of the second. So that means they're back in, right? We just skip the value of the first. We just use a univariate for their likelihood, skip over it. So that's why it happens to be. Here is our model picture. I'm trying to visualize this, right? We estimated the mean vector, we estimated the covariance matrix, and if this model, since this model fits well, we should expect our data to fall somewhere in that nice Taco Bell looking bell-shaped curve. Was it the Taco Bell curve? Wouldn't that be awesome? Remember, this is like 10 years ago, I'm dating myself now, way more than 10. This is in the 90s, I think. One of the first April Fool's Day's jokes on the internet was that the Taco Bell had bought the naming rights to the Liberty Bell in Philadelphia. It was like the Taco Liberty Bell. Anyone like Taco Bell? I have a love-hate relationship with it. It's nasty, but I love it. I hate that I love it. Anyway. Okay, so if I were to, what does that mean? If I were to talk about all our data should be up kind of in that, if we were to look at this, here is a scatter plot of performance and perceived usefulness, right? There is performance, there is perceived usefulness. Remember the contour lines that I showed you last time? That is the kind of the height of the distribution. I've superimposed them on top of this to make it say, what we should see is most of our data should be in most of these lines, and it does look like that, right? Our scatter plot and our lines sort of kind of have a nice shape to them. Of course, I don't know what would be, I haven't shown you what would be bad fit yet, so this is sort of kind of subjective. They're not all under the lines, but remember the distribution goes off into infinity in each direction, so they're still, it's just where R hasn't drawn contours for it, right? So, knowing that this is the best it can get, that's kind of our target. And any other model that we try out should fit just as well as this. Okay? So it's like, well, what would we try out? Why would we try things out? And here's why. So that was 2 variables. We had 5 terms. This is a plot of, if you, on the x-axis of this is the number of outcomes, the number of dependent variables in one of these multivariate models. Conditional MVN. Right? So there's 2. Take a look at what happens. On the y-axis, this is the number of things that the program has to estimate. Oh, this chair, I might fall over. That would add to the fun in class. So the mean vector, every time you add a variable, you add one of those. Every time you add a variable, you not only add one variance, you add a covariance with all the other terms. So you get this bendy shape right here. It essentially is a quadratic function. As you add more variables, you add more things you have to estimate. And I think I mentioned this last week. Every time you have to estimate something, that takes sample size. That means power, right? If you estimate everything, your power is shot. Right? The more things you estimate, the harder it is to find effects on any of them. Right? So, sometimes this is called the curse of dimensionality. I don't know if you've heard of this before. It makes me think of, for whatever reason today, it makes me think of Indiana Jones. I don't know why. Kind of like that movie. Even like the original, not, you know, or one of the first few, not this later. Lack of creative. We need to reinvent franchise Hollywood that we're in mode that we're in now. Sorry, I hate most movies. I know that sounds crazy. The curse of dimensionality is that every time that you add an outcome, right? We think of, oh, multivariate data, it's where the answers are, it's where we really have to study things, but every time you add an outcome, it becomes harder to answer the questions because you have to have that much more data to estimate everything. Right? So you get small power. We actually run into estimation problems. I don't know if you've ever had this. If you have just a limited number of people, try to get a covariance matrix like in Lavaan to work and it won't converge or something along those lines. Some of the common solutions to this, there's different strategies for solutions, depending on the field you're in. But pretty much all of them boil down to some type of constraint or assumption made about the covariance matrix. Covariance matrix is the problem. It's the thing that's the red line is the covariance parameters. The black line is the mean vector. Right? We can add one at a time, but that accelerating thing that's going on in covariance, we really want to get under control. So we find a way to figure out putting in a different covariance structure for all of our parameters. What's different? Well, there's a lot of them. I'm going to show you some not because these are things to dwell on, but just the concept of something different than everything. Right? What's a little different than everything? Well, sometimes last week we talked about what happens if there's no covariance. What if we set it equal to 0? We're assuming our variables are independent. Well, we could test that. We could check it, but that is a structure. That is a constraint in the covariance matrix. So each of the ones we're about to dwell on, and each of the ones in part 2 of the homework, there are 4 models in part 2. The third one is saturated. The first 2 deal with constraints of the covariance matrix, and the last one does a constraint on the mean vector. Right? They're just constraints. They're assumptions you might make. Each one of those are just different structures that we just pulled out of thin air. They're not anything more than just to say that we can do it. That's it. They're actually, I lie about that. There are actually two there that you'll be, wow, really? One is repeated measures ANOVA, one is MANOVA. But I'm not going to go into which one's which. But you're actually doing both of those in your homework this week. And I didn't even tell you that. You're getting the multivariate course for the price of one. 2 courses for the price of one a day. Boy, I'm really loud. They must, sorry. Nice. Probably not for me. So anyway, in each of these structures, though, they have to fit as well as the unstructured model. That's the goal, right? Whenever you get away from the unstructured model, it has to fit as well as. That's your alternative hypothesis. So here we go. Blah, 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 blah. Blah, 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 blah. Let's do this. Here we go. Okay. The details of matrix algebra were there. You are welcome to follow them. They're really just tying this towards things that you might see in a mixed models course or a multivariate analysis course. But for now, let's dwell on what we need. Here are very common R matrix structures. R matrix being the residual covariance matrix in our empty model. Something called, we're at unstructured or saturated. That's what we've been talking about. You can come up with something called variance components. We talked about this last week. That is the structure where the variances are set to be equal for each variable, and the covariance is set to 0. This doesn't look like the case for ours. We had a big variance of usefulness and a small variance of performance, so it probably, just looking at it, probably isn't the case, but we could try it. Independent variables essentially says, okay, the variables are independent, but we're going to estimate each of them to have a different variance. Right? A little bit more, less stringent. Right? Independent variables, if you put a variable into an analysis in Lavaan by itself, that's what it's assuming when it starts. Right? We're going to estimate its variance to be separate, but keep it independent of all the other ones. Compound symmetry is an odd word. It's a thing that's dying. I wish it would hurry up and die. But has anyone ever done repeated measures in ANOVA? Wow, nobody. Awesome. Then this doesn't apply. No one's ever said those words to you in your life. Repeated measures ANOVA. Yeah? Jennifer, thank you. Restore sanity. Jake, maybe? No, you're smiling. No, never heard those words. That combination's never been uttered.
Well, I've heard them.
Oh.
Never did it.
Repeated measures ANOVA is when you have a within subjects factor. Essentially, you're taking multiple measurements. And repeated measures, that's the repeated measure. You may have within subjects effects. You may have between subjects effects. You're doing analysis of variance on the within side and between side. The assumption that you invoke is something called compound symmetry, which is sort of like the variance components, remember, where each variable has the same variance, but we also estimate a covariance, and each pair of variables has the same covariance. So everything is the same correlation and the same amount of variation. It doesn't make sense in most data, but if you're like taking measurements of, I don't even know, resting blood pressure, I don't know, something like that, you know, measurement 1, measurement 2, measurement 3. If I'm not moving, if like I'm fast asleep and you're taking my blood pressure, right, it should have about the same, I guess, depending on what stage of sleep. I don't know. I'm trying to make this so that it doesn't make a lot of sense, right? Anyway, so I'm going to show you each of these just in the context of these are 3 different structures. We have to make it work, to use the analysis, we have to compare it to the unstructured model to see that it fits. Here is model 3, variance components. Right? This is the model where the variances are constrained to be equal. In Lavaan syntax, that is where that term in parentheses comes from. Right? You essentially specify the model as you would, and for every parameter you want to set equal to another one, you give it a label. In my case, my label is var. You put the label in parentheses, and you make it look like it's multiplying the value. Right? So if you remember the syntax, if I wanted to estimate the variance of performance, it's this line without the var part in front of it. But when I want to make it so that I estimate the variance of performance and usefulness, and I estimate them both to have the same value, I give them the same label in front. And that tells Lavaan, oh, I want the same value in both places. And sure enough, in the output, right over here, it tells me the label I used. I called that var. And sure enough, look at that. Both parameters, standard errors, z-values, p-values, all those are the same. Links them both together. Okay. Similarly, if you put a number there and then put a multiple by it, that's not a label to Lavaan. That's an actual numeric value. So by doing a 0 times use, I literally put a 0 up there in the covariance. So the estimate says 0, but you don't see standard error, z-value, or p-value. That says we didn't estimate that. That was set by constraint. So this is different. If you're familiar with M+, M+ will actually give you like a standard error of 0. So your z-value is 999, some obscene term that if you could divide by 0, it would pretend is. I don't know where it comes from. Anyway, Lavaan at least allows it to not even show up. So that is kind of a silly model. I don't think it's going to fit, but here's an overlay of the plot. To make it fit, this is our data. All right, I had to make this model fit in a path diagram. These data from the picture before, it looked like the data were spread out in the circles. The circles are the same sizes, because there's no covariance and the variance in each dimension is the same, to make it fit on here, I had to tweak the axes. All right, so the limit of this thing is like this lower contour is now like below 0 for one of the variables, right? Where it didn't go there before. But what you see is our data is smushed in the middle here, and our circles don't have a lot of data in it. This is not good fit. Okay? So just by looking at that, you can say, hey, our model, when we said, oh, I'm going to assume this variance components thing, whatever that means, we're making assumptions about the data. They have to fit. Let's see, did it fit? No. Haven't quite quantified fit. Yes, Lou?
May I ask, in what kind of situation this model would be a good fit?
If you are in a, if you've never taken a class on multivariate or hierarchical linear models, if you treat, if you have an HLM, maybe you have a, but you don't treat it that way. It's essentially this. Maybe this is two different groups of people, or two different values from a different group. This would be if you assume that they're not, the group has no effect. It's like having no correlation within the group itself. So. Otherwise, I wouldn't go. There's not a lot of reason for this. Other questions? Okay. How about independent variables? Now, this is where we estimate both variances. We leave the covariance at 0. So the syntax just takes off the label. You don't see the var in parentheses ahead of it, which means it estimates both variances. We set the covariance equal to 0, which means we still have that 0 part in it. Now you can see how you can mix and match parts of the syntax. So that second part of homework 2, essentially you're going to have to do that, right? You have to sometimes do variance components, sometimes do compound symmetry, unstructured, and so forth. Here's how it fit. Whoa, that fit better, right? Better. I should have made the y-axis the same. That would have made it different. I think I had a hard time. It kept breaking on me, so I gave up. Sorry. I quit. I'm sorry. I'm a quitter. What about compound symmetry? That's when the variances are equal and the covariances are equal. Here, the variances being equal, we have both of the labels show up again. I actually put the label in the covariance spot, even though we have one covariance. It's going to be the same value it was before. Basically, this is model 3 from lecture, the independent variables plus estimating the covariance. And here's how it looks again. Ugh, not good. So here is our saturated model. Again, here are all of our estimates. So you can see we've got 4 different models for everything. And here's how it should look. We haven't done any model testing. We're just thinking philosophically. We want, if we go and put some type of assumption in, and by assumption, I mean your hypothesis. When you go and do your data analysis, you've got an assumption that you're putting in. It needs to fit as well as H1. I'm just trying to provide the visual description to go back to when you think about what we're doing in our modeling process. How we doing? I know it's so exciting. This is not your favorite, right? To me, I love this stuff, though. Sorry. All right, so how do we tell if model fit works, aside from using your eyeball? What? Believe me, there are some fields where people use their eyeballs for model fit, or some models where people do. But for us, at least, we actually have good methods. But why do we need to worry about model fit? Here is the key. If you take a model that does not fit the data, your parameter estimates may be biased, right? So if you think a correlation is 0.3, it may say it's 0.3, but the true value may be something like 0.2 or 0.1 or not significant. Right? Your standard errors may be biased. That's even worse. That means you're starting to get type 1 error rates. Type 1 error is like the crack cocaine of statistics. It's really addictive, right? Because if you're in a model, like if you're doing your dissertation, you've got this hypothesis, right? The quant students here are a little bit different because we make our own data, but if you're like collecting data for your own dissertation about some experiment or some design that you want to do, you want that p-value to be small, right? A type 1 error is when the p-value is small and it shouldn't be, but it gives you a dissertation either way, right? So it's like dangerous. Like if you're concerned about the truth, you should be concerned about model fit. If you're concerned about if you want a small p-value, I can help you with that, right? Sorry, I was having these conversations with my colleague. There was a previous faculty member. Never mind. We can go down there. The bottom line is, if you don't get model fit, whatever you're saying about the model may not be appropriate, right? So you don't want to take a model that doesn't fit and start claiming it's changing your research base or whatever else. So model fit is the first step of everything that we do in a model that has more than one outcome. Multivariate models, model fit. The model fit, the model fit, the model fit. It's like the first, it opens the door. All right? But that said, not all good fitting models are things worth reporting. You can have perfect model fit and absolutely null results. Like nothing. Right? No story, but it fit great. Right? That is also a common thing that we see in I see, and actually this is not you. If it's hard on you being in this class, imagine being the people you look up to, editors of journals. I've been on papers where, they've said model fit's good, therefore it must be good. And it's like, no, really, the model fit is great. All correlations are equal to 0, right? There's no story to talk about. There's nothing going on here aside from that, right? So model fit is like, if you were in math, you'd say it's necessary but not sufficient to describe a result, right? You need model fit just to look at the results. Once you get to the results, there may be nothing to talk about. Right? If we're talking about Indiana Jones, it's like when it's like when you take the little medallion and the ball starts. It's necessary to have an action movie. So, model fit. What we're going to talk about is based on these multivariate normal or conditional multivariate normal models. It's basically when you assume your data follow a continuum. In multivariate normal land, it's where we put the label SEM for whatever reason, or CFA or path analysis. It doesn't have to be there. But in MVN world, it makes model fit relatively easy because we can compare it to the saturated model. There's always a saturated model. All right? We know what it should be. If you're not in that world, it's very different, but we're not going to talk about that until the end of class. So there's not a saturated model. That's the problem. It's really hard to find model fit when there's nothing to compare it to. The nice thing is that all models that we're going to do, all hypotheses you have, are nested within the saturated model. Now remember the word nested from last week? Likelihood ratio tests are used with nested models. Right? So if you have your hypothesis, right, you go and estimate your hypothesis, you can form a likelihood ratio test between your hypothesis and the saturated model always. And sure enough, actually Lavaan's output does that for you. That's one of the methods of model fit that we use. Sure enough. So that's nice. And actually what we're talking about with respect to model fit is we talk about it at a global level, which is all of my model fits all of my data, or it's good enough for everything. And what we'll end up seeing is that if usually model fit when you start off isn't good globally, and you want to sort of maybe change the model slightly to make it fit better so you can talk about it, you'll have to go into more localized model fits. So maybe a pair of variables, like their covariance isn't being fit well, or another pair of variables, or maybe the mean vector for some reason, although usually mean vectors are okay. But I'm over time by 30 seconds. I'm sorry. Please take a break, 10 minutes, and I'll see you in just a little bit. When I promise you a break, you can set your clock by it usually. So, and that's not just for you. That's for me too.